I'm going to begin today's lecture with a story that has nothing to do with today's lecture. Many years ago, before we were married, I took my wife for a romantic dinner at the International House of Pancakes. While there, we coincidentally sat next to an old acquaintance of ours, and he and I began to exchange a few memorable stories and anecdotes. In my typical social manner, my voice volume began escalating, and a guy who was seated 2 tables away from me during this looked over at me and told me very bluntly, "Can you stop talking so loudly?" Now, at the time, I was kind of a young and defiant individual. I looked the guy up and down, noticed that he was wearing one of those little visor hats, you know, the ones that kind of look like ball caps, except there's no top to them. I've always hated those things. Anyway, I said to the guy, "I'm sorry. I didn't mean to interrupt you and your hat." I was lucky that that guy and his group of 5 large friends didn't kick my butt that night. Now, a year or 2 later, my wife and I, now married, were dining at the same restaurant. She brought up that experience. I laughed, still a little surprised that the guy had enough guts to blatantly yell at me, a person whom he didn't know, telling me to be more quiet. Then I had an idea. I said to my wife, "Honey, wouldn't it be funny if I just was as rude as that guy and I just turned around and told whomever happened to be sitting behind me to stop talking so loudly?" As she looked over my shoulder in response to this at the group of people who were sitting in the booth behind me, and her eyes seemed to almost be daring me to tell them to stop talking so loudly, just as I'd proposed, even though they weren't really talking loudly at all that I could tell. I could read my wife as a book, so I turned around to face that booth, intent on following through with this challenge. I was going to tell them to stop talking so loudly. Now, my jaw dropped in surprise at what I saw. In an almost statistically impossible way, it just happened to turn out that all of the people who were sitting at the booth behind me were all conversing jubilantly with each other in sign language. I mean, what are the odds? If there was ever a group of people that was less deserving of a rebuke to be quiet, it was this one. Now, as a result, on this particular occasion, I just turned around and shut up. Today is my second presentation designed to help students prepare for standardized exams. Here are the things that I want you to know how to do by the end. Define chirality, dextrorotatory and levorotatory. Assign RNS configurations to molecules with stereocenters. Determine whether stereoisomers are enantiomers or diastereomers. Designate an alkene as being either E or Z. Identify Meso Compounds. Identify how many possible stereoisomers can exist for a given compound. Know that Racemic Mixtures and Meso Compounds are achiral. Define and identify epimers. And contrast between relative and absolute stereoconfigurations. So tell me, guys, what is the difference between these 2 molecules? And does this difference really make them different? Well, now, of course, you guys might remember from a lecture that we had last semester that the compound on the right is called R-thalidomide, which was used in Europe during the late 1950s to treat morning sickness in pregnant women. The compound to the left is S-thalidomide, which causes birth defects. These 2 enantiomers, which were at that time being administered in a racemic 50-50 mixture, definitively relieved morning sickness among those who took them. But, unfortunately, this mixture also caused many babies to be born with malformed limbs. Why? Because any molecule with a stereocenter is chiral. Most of the enzymes in all living things, including people, are also chiral, and therefore have the ability to discriminate between enantiomers. Thus, one enantiomer will fit into an enzyme in a certain way, and another enantiomer will fit into the same enzyme in a different way, or might not fit at all, or might fit in the enzyme in a different place. And thus, one enantiomer often will behave biologically in one way, and the other will behave in a completely different way. Now, this might seem slightly tangential, but I want to introduce you guys to this property called chirality, often referred to also as optical activity. You see, some molecules will rotate plane polarized light when they're placed in a special machine called a polarimeter. Such molecules are said to be chiral. Molecules with tetrahedral stereocenters are chiral. There are also other chiral molecules without tetrahedral stereocenters in them as well, such as cis-trans or EZ isomers. Chiral molecules rotate plane polarized light. We say then that such molecules are optically active. Molecules that rotate plane polarized light clockwise are called dextrorotatory. Molecules that rotate plane polarized light counterclockwise are called levorotatory. Now we get back to stereocenters and enantiomers. You see, an atom that's bonded to 4 different things in a tetrahedral geometry is called a stereocenter, or sometimes a chiral center or chirality center. The mirror image isomer of a tetrahedral molecule A, shown here, is actually a different molecule because it can't be superimposed onto molecule A. Non-superimposable mirror image molecules are called enantiomers. Here's a picture of another picture of non-superimposable mirror image molecule. Once again, they are called enantiomers, and they are not the same molecule three-dimensionally speaking. Now, because enantiomers are actually different, we have to have some way of naming them to be able to distinguish one enantiomer from another. We use a system called the RS naming system. I'll now guide you through the steps of the RS naming system, with which you're probably already quite familiar. Step 1, find your stereocenter atom. Step 2, prioritize the 4 different substituents or appendages coming off that stereocenter atom. Now, the highest priority is the highest atomic number. Now, if there's a tie, that is, if you go one out and they tie, you keep going out one bond at a time until you break the tie. Now, isotope atoms have the same atomic number. But if you have isotopes, a higher atomic weight is higher priority. Thus, if I have a deuterium versus a hydrogen, deuterium is considered a hydrogen or a higher priority. Step 3, number your substituents 1, 2, 3, and 4, where 1 is the highest priority, 2 is the second highest priority, and so forth. Step 4, point the lowest priority substituent, priority number 4, three-dimensionally away from you. And step 5, make a circle going from substituent 1 to 2 to 3. And remember that clockwise is R and counterclockwise is S. Now, this might seem like a very long process, but once we do it several times, it starts to become a little bit more comfortable. So here is a stereocenter in which we have identified or prioritized the 4 different appendages or substituents coming off of it as 1, 2, 3, and 4. Now remember, the steps that we have to go through is we have to point group 4 going three-dimensionally away from us. So if I were actually staring at this, I would have to imagine what it would look like if I were staring at it from underneath the crotch of this 3-legged animal, with group 4 pointing away from me. So here is what I would see if I were staring up the crotch of this 3-legged tripod, so to speak, and group 4 were pointing away from me. I draw a circle going from 1 to 2 to 3, and you'll notice that it goes clockwise. We remember that clockwise is R. One way of remembering that is that if you're turning right, or R, in a car, you turn the steering wheel clockwise. Now over here we see this enantiomer. We've categorized or prioritized all of these substituents, 1, 2, 3, 4. We point group 4 three-dimensionally away from us, and now we go in a circle from 1 to 2 to 3, and you notice that it's counterclockwise. We can remember that counterclockwise is S, because if we're steering a car's steering wheel to turn left, or S, that's counterclockwise. Now I realize that left doesn't start with the letter S, so often I think of myself as wanting to turn my car sleft. If I want to turn right, it goes clockwise. If I want to turn sleft, it's counterclockwise. Hopefully that makes sense to you. It certainly does to me. So here's a lecture problem. I want you to assign R or S configurations to the following molecules. Let's take a look at this first example to the left. What I'm going to do is find my stereocenter atom, which is this one right here, and I'm going to go out one bond at a time and prioritize all of the groups to which it's attached. You'll notice if I go up here, I've got a bromine, I have a hydrogen, I've got a carbon, and I've got a carbon. Who has the highest atomic number and hence the highest priority? It's bromine, number 1. Who has the lowest? It's hydrogen, so hydrogen's going to be number 4. But you'll notice that here I've got a carbon and a carbon. They tie. So what do? Well, I go out one more atom. This carbon is attached to a hydrogen, and this carbon is attached to an oxygen. The tie has now been broken. So which of these two groups has a higher priority? This one over here stuck with to the oxygen. This is priority group number 3, and hydrogen is, of course, the loser, number 4. Now what I'm going to do is I'm going to draw a circle going from 1 to 2 to 3, and you'll notice that from this perspective it looks like it's going clockwise. However, you have to keep in mind that right now the lowest priority group is pointing three-dimensionally towards us. If it were pointing away from us, in other words, if we were sitting on the other side of this computer screen staring down the crotch of this tripod, indeed 1 to 2 to 3 would actually be going counterclockwise, which means that this stereocenter is S. Now I'm not going to do the rest of these examples here for you, but I'll invite you to try them on your own. Now here's a more challenging question. Are the following pairs of molecules enantiomers? Let's take a look at this first one. You might remember from the example we just did that this stereocenter is S. What is this stereocenter over here? Well, we have group 1, group 2, group 3, and group 4 ordered according to priority. If I trace a circle going from 1 to 2 to 3, once again it looks counterclockwise, but you have to imagine what direction it would be going if I were three-dimensionally sitting on the other side of this computer screen and group 4 were pointing away from me. It would actually look clockwise to me, which means that this is R. So these two molecules are enantiomers. Now that might sound like a ridiculous waste of time to assign R and S to these two, because you can see obviously that they are mirror images of each other. If this molecule to the left were staring in a mirror, the molecule that it would see in the mirror would be this molecule to the right. They are non-superimposable mirror images, which means they are enantiomers. Now, that's very obvious in this example, but what about this example over here? Now, in this example over here, these molecules are not drawn in a way that makes it super obvious that they are mirror images or aren't mirror images of each other. I can't tell looking at them. So what I'm going to do is assign R and S to each of the stereocenters. If they are opposites, then they are enantiomers. If they are the same, then they're actually the same molecule, just where one has been flipped around three-dimensionally relative to the other. So let's find our stereocenter. Here's the stereocenter. I'm going to prioritize my 4 groups. I've got oxygen, hydrogen, carbon, carbon. Who's the winner? Oxygen. Highest atomic number. Therefore, he's the winner. Now I've got carbon and carbon. They tie, so I have to go out to break the tie. This carbon I go out to a hydrogen. This carbon I go out to an oxygen. Tie is broken. Who wins? This branch. This is branch number 3, and the loser, the lowest atomic number, is hydrogen, 4. So now I trace a circle going from 1 to 2 to 3. Now it might not look super obvious which direction that is, but you have to imagine what direction this would be if you were sitting underneath the crotch of this tripod staring up, so that group 4 were pointing away from you. Group 4 is pointing away from you and you're staring up this like an auto mechanic who's sitting underneath a car. Going from 1 to 2 to 3 would indeed be counterclockwise, which makes this stereocenter S. Remember, counterclockwise is the direction you turn your wheel if you're turning your car left. Remember, S is for left. Let's do the same thing for this molecule over here. Priority group number 1 is the OH, 2 is this carboxylate group, 3 is this CH3, and 4 is here. Now in this particular molecule, it is drawn on the page with group 4 going away from us already. So I don't have to imagine what it would look like going away from me, because it already is. I trace from 1 to 2 to 3. That's counterclockwise, so this is indeed S. So what are these two molecules relative to each other? They're actually the exact same molecule. If you were to build a three-dimensional model using marshmallows and toothpicks or a model kit of each of these molecules, you would see that if you just turned one around in your hand, you could get each one of these atoms to line up perfectly and stack up on top of the corresponding atoms in the molecule to the left, because they are the same exact molecule. The take-home is this. If two otherwise identical molecules have opposite RS configurations, then they're enantiomers. If they have the exact same RS configuration, in other words, if this guy's S and this guy's S, then they're the same molecule, just drawn three-dimensionally funny-looking relative to each other. Now I'm going to ask you guys an even harder question. I want you to tell me if each of the pairs of molecules here are enantiomers. Now I'm going to start out by just looking at this pair right here. I hope you guys can see that the molecule on the left, if he were staring in a mirror, would see the reflection, or his reflection would look exactly like the molecule to the right. These two molecules are obviously enantiomers. They are mirror images of each other that aren't superimposable. That's really easy to see the way they're drawn. Over here, though, these molecules, that is not super obvious. This guy to the right is not the mirror image of the guy to the left, in every way at least. So what in the world do we have to do? What we're going to do is we're going to label each of the two stereocenters in these molecules as being R or S. Let's start with this stereocenter here. I'm going to go out one atom at a time. I've got a bromine up here, a carbon, and a hydrogen. Who wins? Bromine. Now the carbon and the carbon tie, so I have to go out one more atom to break the tie. I go out here to the hydrogen, and I go out here to the highest atomic numbered atom, which is the chlorine. Chlorine wins over hydrogen. So this whole branch to the right is considered priority number 2. This methyl is considered 3, and the hydrogen is always the loser. If I were going 1, 2, 3, it looks clockwise, but remember, if I were on the other side of the screen and this hydrogen were pointing away from me, it would actually be counterclockwise. So this stereocenter is S. Now I'm going to determine if this stereocenter is R or S. So I'm going to ignore all those numbers and just remember that that stereocenter is S. Let's go over here to this stereocenter. I go out one atom at a time. I've got a chlorine, a carbon, an oxygen, and a carbon. Who wins? Chlorine wins. So now who's second place? The oxygen, obviously. And now I've got a carbon and a carbon who tie. I'm going to see if I can break the tie. This carbon stuck to a bromine. This carbon stuck to a hydrogen. So the carbon to the left is group number 3, and the carbon stuck to the hydrogen, this methyl, is group number 4. Conveniently, in this particular drawing, group 4 is pointing three-dimensionally away from us, so I trace from 1 to 2 to 3. It's counterclockwise, so this stereocenter is S. Now, if you do the same exact convention for each stereocenter over here, you'll notice that this stereocenter here is R, and this stereocenter is S. So what are these two molecules relative to each other? If I'm just looking at this stereocenter right here, it's S in this molecule, and over here it's R. That seems to be opposite. But what about this second stereocenter over here? It's S here, and in this molecule to the right, it's also S. So these two molecules are not exact opposites of each other. They're half opposites. We call this type of molecule a diastereomer. So these molecules are diastereomers. So what's the take-home? If two otherwise identical molecules have more than one stereocenter in them, then one of 3 scenarios will occur. If they have the same RS configuration at every single stereocenter, then they're the same molecule. If they have the opposite RS configuration at every single stereocenter, then they are enantiomers. And if they're anywhere in between, then they are diastereomers. Now, one more thing I want to show you is this. Standardized exams frequently ask you to determine how many different stereoisomers a specific molecule can have. The answer to that question depends on how many stereocenters the molecule has, according to the following formula. So the number of possible stereoisomers equals 2 to the nth, where n is the number of total stereocenters in the molecule. Now, the application of this knowledge will become more apparent later on, but I want you to tuck it away in your brain for later. Now let's get to another problem. Is each pair of molecules here a pair of enantiomers, diastereomers, or just the same molecule drawn in a different orientation? Next question. How many possible stereoisomers are there of each of these compounds? I'm not going to give you the answer, but I promise I'll give you this question in class. And now another thing. We chemists have a special name for diastereomers that have the exact same RS configuration at every stereocenter, except for one. This name is epimers. So if you look at these two molecules, you can see that they have the exact same configuration at every single stereocenter except for this one. Can you guys see that? They look exactly the same at every stereocenter except for one. Technically, these two molecules are diastereomers. However, we just have a special name that we give to molecules that are different, that are diastereomers, but are only different at one stereocenter. We call them epimers. So once again, epimers are diastereomers that only differ three-dimensionally at one stereocenter. That's another tidbit I want you to tuck away for later. Now I need to tell you that there are two other types of stereoisomers that are also called diastereomers. Those are EZ isomers, like the ones shown here, and cis-trans isomers. And you might remember from my last special topics video that cis-trans isomers are also sometimes called geometric isomers on standardized exams, although this is an extremely outdated and archaic term that should be expunged from all use. But it's still used, unfortunately. Now I want you to imagine that we have a molecule A shown here. I'm going to use my imagination to draw the enantiomer of A right here. Now, what do you notice about A's enantiomer? Let's look at it. Now here's the enantiomer. Now, do you agree with me that if this guy A were staring in the mirror, what he would see is this? So this molecule over here is the mirror image of A, isn't it? It is. I mean, this looks just like the reflection of A. But what do you notice about this enantiomer of A? Well, if you look at it for more than 5 seconds, you'll notice that the enantiomer of A is actually the exact same molecule as A. Isn't that true? So you could imagine I could take this molecule and plop it on top of this one. They look exactly the same. So what the heck does that mean? Well, as it turns out, if you have a molecule like A that has a line of symmetry going down the middle of it, then it is achiral. That is, it doesn't rotate plane polarized light. Compounds like A are called meso compounds. Meso compounds enantiomers are actually the exact same molecule as the meso compound itself. So if you have a meso compound and you draw its enantiomer, you'll actually discover that its enantiomer is itself. So meso compounds, that is any compound that has a line of symmetry going down it somewhere, will indeed be achiral, and its enantiomer will be the same molecule as itself. Let's look at some problems. I want you to tell me, are the following compounds meso? I'm not going to give you the answers, but I'll let you figure it out for yourself. Now on to something else. As I mentioned earlier, if you have a 50-50 mixture of two enantiomers, it's called a racemic mixture. Now racemic mixtures are also achiral. That is, they don't rotate plane polarized light. Why? Because if you have one enantiomer inside a polarimeter, it will rotate plane polarized light in one direction. But the other enantiomer will rotate it in the opposite direction. Now, if you have an exact 50-50 mixture, one enantiomer rotates it in one direction, the other enantiomer rotates in the opposite direction by the exact same amount, so they cancel each other out. So once again, racemic mixtures are achiral. They don't rotate plane polarized light. Now if you happen to have a mixture that has one enantiomer in a larger amount than the other, it's called an enantiomer-enriched mixture. Now we arrive at our actual questions. As per usual, I'm not going to answer any of these questions here, but I want you to consider and think about them. I will give you these questions in class and require you to answer them. And of course in class, you can ask me more if you have questions or don't understand them. Question number 1. Which of the following do not show optical activity? I will let you on your own read these options and decide. Question 2. How many stereoisomers are there for the molecule shown here? This is, of course, a Fisher projection of a sugar. Question 3. Which of the following best describes the molecule shown here? Does it have one chiral center, two chiral centers? Is it achiral or is it a meso compound? Question number 4. Which of the molecules to the right is a Z alkene? Now, I haven't taught you in this lecture how to determine if something's Z or E, but that is something that you should remember or review prior to taking standardized exams. Next question, which of the molecules shown to the right are diastereomers? Next question, a sequence of reactions known as the Vol degradation removes the aldehyde group from carbohydrates as follows. So you can take a molecule like D-glucose, subject it to these sequential reactions, and it will remove this aldehyde and convert this OH into a double bond to that carbon. And you see that? It effectively shortens the chain. As it turns out, Vol degradation of both D-glucose and D-mannose gives the same product, D-arabinose. What does this suggest? And I'll let you read through these options and see if you can figure it out. Next question. The reaction shown to the right, here it is, results in which of the following? A retention of the relative configuration and a change in the absolute configuration. A change in both the absolute and relative configurations. Retention of both relative and absolute configurations, or retention of the absolute configuration and a change in the relative configuration. This is another topic I have not taught you in this lecture, but I will teach you in class. And last question. Optically active molecules that rotate light clockwise are considered to be which of the following? Now that ends our presentation today. I hope that you've enjoyed it, this review of stereochemistry and polarimetry. Man. So stay tuned for our next lecture, where we will discuss even more important topics to help you guys prepare for standardized exams.